us for our first stargazing lecture of 2025. Sorry about the postponement last week. It seemed appropriate given that a lot of people were struggling in the community with the impact of the fires from the last couple of weeks. So we decided to postpone to tonight, and we've got great weather to help us make it through a great evening tonight, and a great speaker as well. So I'm Dr. Cameron Hummels. I'll be your host for this evening's activities, and I'm just going to give a quick layout of how tonight will go, as well as some announcements about upcoming events that we'll have in the next month or so. So if you've been to one of these before, you know how it goes. After a few brief moments of announcements, I'll introduce our speaker, who's going to talk for about 30 minutes, all about the exciting topic of potentially traveling at faster than light speed and some of these science fiction-y possibilities and how well they cohese with the rest of physics and relativity. So after the 30-minute presentation, we'll take a handful of questions from the audience, and then we will kind of have a brief intermission. During that intermission, you're free to stick around. We'll have a Q&A panel that begins in here and goes for about an hour or so, consisting of the speaker, myself, and two other members of the department who work on a variety of different topics in physics and astronomy to answer your questions on whatever topic that you may have, whether it's related to the content of the presentation or if it might be something totally different, something you read in the news about a comet or a black hole or whatever, and we can do our best to answer that question. At the same time as our Q&A panel, we'll have telescopes that are being set up right now on the athletic fields behind us, and to reach those, you can just go out the front door and follow the signs around the building and go onto the athletic fields. There are 4 telescopes set up tonight. You may have read in the news about the planet parade that is going on. It's pretty cool, but it's also not super, super rare as the news might have you believe. But what it means is that you can see Jupiter, Saturn, Mars, and Venus all up in the sky. And there are 2 other planets, Uranus and Neptune, that are up in this portion of the sky in the evening, but you have to have a telescope to be able to see them because they're too faint for the naked eye. So we'll have telescopes pointed at a couple of planetary objects, probably Jupiter and Mars, and then we'll have a couple of telescopes pointed at deep sky objects like the Orion Nebula, a star-forming region in our own galaxy, or the Andromeda Galaxy, our nearest kind of massive galaxy to our own Milky Way. So you're also welcome to go out and check out the telescopes and come back in and ask a question of the panel, or vice versa. Both will go until about 9:45 or so. So feel free to play it by ear and go between the two. These events take place once a month. Our next one will be February, oh no, I just figured it out. Oh, Valentine's Day. It'll be on February 14th. So if you've got a date and you want to come and look through telescopes on your date, feel free to show up, but you also don't have to be on a date to come to our event. You could just come anyway, but it will be Friday night, 3 weeks from tonight on Valentine's Day, February 14th. And our speaker for that is going to talk all about the explosions that erupt around active supermassive black holes in the centers of galaxies. It's one of the postdocs in our department who was recently featured in the New York Times and a bunch of news for this discovery of this outburst and this jet of material that was flying away from the center of a galaxy that he detected. So his name is Dr. Martijn Ooi. He's Dutch, and he's going to talk all about that. So very romantic for your Valentine's Day needs. And in addition to this series of events, we have Astronomy on Tap that takes place at a bar in Old Town Pasadena called the Doghouse Beer Garden. It's all outdoors, and it features a couple of 15 to 20 minute public presentations on different science topics. Our next one of those was meant to be this coming Monday, but because one of the speakers is sick and because it's supposed to rain, we postponed it 1 more week. So it's going to be Monday, February 3rd, and at 7:30, and you can see the poster in the hallway, or it's on our website or all of our social media sites. So that should be great. That should be really good. And there's astronomy themed pub trivia, and there's telescopes, and there's live music. It's a fun time. So, and I should also make the announcement that in a month's time, we will be helping put on the Dark Sky Festival that Death Valley National Park is hosting. That's a few hours drive, so it's a bit bit of a drive. It's about 4.5 hours to get to Furnace Creek from here. However, there are very, very dark skies, much darker than you can experience here in LA County because you're a long ways away from cities, city lights, and light pollution. And that will be February 21st through the 23rd, a Friday through Sunday. It's free to attend. You have to get into the national park. So if you have a parks pass that gets you in, then it's totally free. Otherwise, you have to pay for entry. And there will be all sorts of events. There will be 2 astronomy on taps that we're hosting. There will be a number of telescope sessions on Friday and Saturday nights with like dozens of telescopes set up, and you can wander around and look through this telescope or look through that telescope at whatever targets are being shown. There will be a bunch of public level science lectures on a variety of topics. We're going to host an astrophysicist Q&A panel for an hour. There's lots of really cool stuff. So I encourage you to check that out if you are so interested. And a lot of people, I know our group, we're bringing a dozen or so graduate students and postdocs up, and we're going to be camping there. And so you can certainly camp. If you want to stay in a hotel, I think it can get a little expensive to stay in the park, but you can stay outside of the park and it's much more reasonable. So yeah, so it should be fun. So maybe we'll see you there. So I think those are all of my announcements at this point. So I'll introduce our speaker. Our speaker originally hails from Germany, did his undergraduate studies at the University of Göttingen in the center part of the country, studying physics, and then did his PhD in Frankfurt, Germany. Before, when he finished, he got his PhD. He traveled first. He spent some time in New York at the Center for Computational Astrophysics at the Flatiron Institute, and then was a postdoctoral fellow at Princeton and the Institute for Advanced Study, where the institute that's famously shown in the film Oppenheimer, where Einstein was the one of the help found that institute. So Elias was there before he joined our department just recently as one of our junior faculty members. So he's now a professor here. And his research is really diverse, but he focuses a lot on compact objects. So these are black holes, these are neutron stars, white dwarfs, really dense structures that are very massive, where relativity, Einstein's theory of relativity, defines the motion and the interaction of the objects that are in those environments, like accretion disks of stuff falling down onto black holes. And he does a lot of theory and computational work associated with these sorts of objects. So I convinced him to give this exciting talk about really a science fiction topic that does have some seeds in real physics and real life mathematics. So I'm excited as much as you are to hear what he has to say. So please welcome Professor Elias Most.
All right, thank you so much, Cameron. And thanks everybody for coming. Wow, that's a huge crowd. Okay, so I'm going to take you all through an interesting interstellar journey, or at least I tell you what we would have to solve in the future to be able to do so. And as Cameron said, this is a talk given by popular demand. A few months ago, we had so many questions about the warp drive that we felt, okay, maybe we really have to go behind this. Is this real? Is this science fiction? How does that fit in with the picture that Albert Einstein almost 100 years ago painted about how the universe should actually work? And so what we're going to do in this talk is we're going to go from the ground up in terms of physics. We're going to look at some very basic principles of how we move through space and time. And then we're going to see ultimately what would have to be done to make this picture a reality. And what may be the challenges. Okay, in order to build ourselves up for this, we have to sort of take it step by step. Meaning, before we talk about how we travel faster than the speed of light at interstellar speeds, maybe we should talk about something very boring, maybe traveling way below the speed of light. I mean, you all got here somehow. Maybe you drove here by car, you came with the metro, the bus, you cycled here, you walked here. However you came here, certainly you're experts in motion to be able to make it today. And what I want to do is I want to take your daily life experience that you have from doing so and just show you how that actually relates to the basic concepts about relativity. So once you can go home today, you'll basically see many of the things you do are intimately connected to the basic questions about physics and the challenges we have for interstellar travel. There's one thing that will be different, whether you cycle or on your way back you board Einstein's magic subway or metro here. The question is, there is a fundamental difference about your experience that you'd have if you drive back home, if you go, on your bike, or if you travel near the speed of light. And later in the talk, I show you visually what it would look like if you could actually go at light speed. And we'll also see how this baseball and maybe Dodger Stadium play into this as well. And then finally, once we get a feeling for what it means to travel at the speed of light or near the speed of light, then we can really ask ourselves, okay, maybe Einstein was wrong. Maybe we can just travel faster than the speed of light, whatever that means. And then we really are in the realm of Star Trek and science fiction. And I'll show you two popular ways that people have proposed to be in order to do this. And then we even do a hands-on demo for how this would in principle work. One that you can do at home too. So I think that'll be exciting. Okay, so let's get us started. I think one thing to keep in mind is many of the concepts that we're going to discuss today or tonight really are rooted in physics that's already pretty ancient. The original physics concepts I'm going to show you, the ones that we show our own incoming class of freshmen, or many that you have seen either when you were in high school or in college, or maybe on TV or wherever. They're really, really hundreds of years old. And the physics that we're going to talk about was invented about 100 years ago. In 1905, Einstein worked out the theory of relativity, and we're going to see with an experiment what that actually means. And for him, travel at the speed of light was something pretty much far-fetched. I mean, there were almost no cars that were just invented. Maybe people were cycling as well back then, but for sure the train was the fastest thing that they had. And this is why in many things that we'll see, a train is sort of the spaceship of the time. Okay, so we're going to discuss how that fits into this picture as well. The problem is I can't really bring a train in here. I'm going to tell you what you can do if you ride on the metro in order to do the same experiment that we'll do in a second. But because we don't have a train, I had to bring in something more practical. And as you'll see throughout the talk, I've kind of leveraged the magic of AI to create many of these images. And so when Cameron originally posed the question to me, talk about the warp drive, I was like, why don't I have AI do the job for me and generate the entire talk? And so I asked AI, what should I do? And this is what ChatGPT thinks I do all day. I just sit in my office, I think, and in a kind of Platonic or Socratic fashion. It got some details wrong. I definitely have more hair in this picture than I have in reality. And my name is also not spelled this way, right? But ChatGPT was right in one aspect, namely to demonstrate how the principle of relativity works. Putting me in an office chair is a very good idea. And I'll show you why. So the physics that we're going to discuss now is way predates Einstein. This is something that was invented in the 1600s by a different person called Isaac Newton. So maybe we have to dress up a little bit, like so. And the main question there will be if, I take not an apple, as you can see here, and there's an interesting backstory with the apple, by the way. The kind of urban myth goes that he was hit by an apple on the head and suddenly he realized how the universe works. I won't try this out, but what I will try out for sure is I'll take this baseball. I'm going to show you one of the fundamental principles that underlines his theory and that of Einstein. Maybe I show it to you already, even before I get on the chair. Are you ready? Okay. All right, that's it. That's all. That's all what this talk will be about. So basically, the main question will be, if I throw this baseball and I catch it again, is it the same if I just stand here, if I move, if I'm on the subway, if I'm in a car, or if I'm in a spaceship? And those questions are fundamental to the question about relativity itself. What would you see if I just stand here, throw the ball, if I walk, and I throw the ball, or now I need my assistant, if I kind of move at very high speeds to this room? Okay, so I don't have the safety wig that Newton is wearing, but I did bring a helmet, so just in case, just to dress up for the occasion. So let's try this out. Okay, all right. Okay, so what we're going to do now is basically, let me show you. Cameron is going to give me a really, really hard push. I'm trying not to think while he's doing this. Rather, what I will try to do is I'll try the same thing I'm doing now, just throwing up the baseball and trying to catch it again. I want you to pay very close attention.
Are you ready?
All right. Yeah, let's go. All right. Okay. Should we do it again? I need to get back. So, all right. Okay. That's a tough landing. All right. Okay, so the main thing that we saw in the demo, yeah. Oh, so you can, okay, let me just do this. We have again, I mean, our IT skills are limited, basically from, Newton's times. Let me just do that for a second. Okay, so let me share. This is for people joining us online so they can also follow. All right. Let me do that. Switching now, pretty much. Okay, now we're back online. All right. So the main thing I want to highlight is what you just saw. You saw me sort of, cruising around on this chair, throwing up the baseball. But when you actually focused on the baseball was not going straight up, right? It was not doing this. It was more flying in some curved shape. And then ultimately, I was catching it again. And one of the fundamental principles that you learn, one of the first things you learn about physics, or even from your daily life experience, you sit in a car, you text on your phone, nothing really changes. And for me, sitting on this chair, and you're welcome to try it out, by the way, after the lecture, if you just throw the ball, you just throw it upwards, you'll catch it again. It sort of travels with you at the same speed that you're moving. It's a very, very fundamental principle that people realized hundreds of years ago. So those things are equivalent. So if Cameron would put his camera on another chair that would just move at the same speed, basically just see this as if I was at rest. Okay. This kind of fundamental question, where what you see depends on how you look, is exactly what relativity is all about. The only thing that will change is for relativity will suddenly move at much higher speeds. And then something very strange will happen, but we'll get there. So this is kind of the underlying question that will permeate throughout this talk. And then once we understand how this translates over to relativity, then we can really ask the question, how do we break this? How do we get around some fundamental limitation that we find in daily life? By the way, if you want to also try it out yourself in a much more fun setting, you can try this out on the metro. Maybe just take an apple, try it out. It's really fun. Anyway, so what we're going to do now, we're going to kind of accelerate ourselves a little bit. Office chairs are great, metro or trains are great, but what about Einstein's magic subway, right? What happens if we would go near the speed of light and do exactly the same thing? So there's one catch to this. Einstein would not use a regular baseball. He'd use a very special baseball. And what you will see is if he throws that baseball, there's no way that Otani could keep up in any way. Okay, so there's something very, very special that will happen. And the reason is that both the subway and the baseball will travel at or near the speed of light. What does that mean in practice? Okay, so let's say you drive home by car, you go to the interstate or the freeway, and you drive there, and cars are passing you. It says 65 is the limit, but we all know that not everybody drives at the limit, right? You just go a little bit above, or some people do. Now, in Einstein's universe, there's something very special about it. Namely, Einstein says, this is the fundamental speed limit of nature, period. There's no way you can go around this. And so basically he says, you can never go faster than 670 million miles per hour. Okay, so those are the speeds that we fundamentally are talking about. There's nothing that you can really directly measure or feel in real life, just because this is so far detached from everything that we sense around us. There are very specific situations where this number actually determines things that we do. For example, one thing is if you do global positioning, if you use your Google Maps and you want to find your way, that crucially relies on this number, satellite communication, because over those distances, this limiting speed becomes relevant. Or if, in the future, you would want to call somebody on Mars, that would basically tell you cannot directly call with them. You have to record a message because the speed at which your information, your voice can travel there is fundamentally limited. Okay, so that's a very, very important concept. And that observationally, if you have questions, we can talk about it in the question session. There's very, very good motivation for why he thought that would be the case, even with experiments people could do 100 years ago. It's quite amazing. But for now, we just say, this is the law of the land, 670 million miles per hour, that's it. Okay, so what would really change if you were to sit on this train? And so we're going to repeat the experiment. We can't really do this live here because we can't move that fast and we can't fit a train in. And you wouldn't see much if that thing was just, rush by. But what you can imagine is that Einstein sits on this train. He has this magic baseball and he's doing the same thing, just throwing it up and down and catching it. And now with us sitting outside, we try to peek in the train and try to see what would happen. Okay, Same thing we just did here, just that now everything will move at the speed of light. And so we have a little demonstration here in terms of this animation that you can see. So the red dot here, you can think of the baseball. It will go up, down, and then you can see what happens as you travel that fast. So this would just be Einstein inside the train. Would just sit there, would go up and down. And then when you move, you can see the baseball basically bounce up and down, right? You can see it here. That's what would happen. And so you would say, you know, did anything change there? Is anything different? Anybody spot a difference, by the way? This animation is pretty good. There's one thing that has changed. Wonder if somebody spots this. Yeah.
The speed of the ball of light.
Yeah. Exactly. It's different, right? It goes at a different rate. And so if you see the flashing light whenever it hits the ceiling, that also goes at a different frequency. So something fundamentally has changed, even though we just did the same experiment and apparently nothing changed really. So something must happen as you go near the speed of light. So really, this is where we enter the realm of relativity, where we enter the more curiosity side of physics, where things happen that normally you wouldn't think should happen in that way. And so this will be the slide and the next will probably be the most mathematical slide of this talk. So just hold tight. The good thing is we're going to walk a little bit through how you can do this, mainly to show that the only thing you need is math that many of you have seen in high school. It's actually very, very simple to realize that. And then when we've seen that, you can forget about all the math, and we're going to see what you actually see. So we see basically physics in action. So just hold tight for one slide. And so the main thing we have to describe then is basically the motion of this ball as it goes up and down. You can see here is sort of the track that it follows from sort of where Einstein sits at the bottom over to the ceiling. And then we can try and see this connection of, you know, why did the ball move slower? Why did the flashing frequency change? What actually happened? And that's all the math we need. Maybe some of you have seen this. This is very, very old math. It's more than 2,000 years old. It goes back to Pythagoras, telling us if we have a triangle that with a perpendicular angle over there, then we can just take the areas in this triangle. A squared plus b squared equals c squared. Okay, that's all there is. That's relativity, almost, if we apply it to the baseball. This thing plus baseball equals relativity. Great. Okay, so what we're going to do now is we're going to apply this to the baseball case, and then some very complicated looking expression will fall out, and then we just look at visually what that expression means, and then we have relativity in action. Okay, so let's translate this complicated picture over. So here is sort of the height that the baseball travels, called b for baseball. Okay, so just do that. This is b. Now, while the baseball is going up, the train is moving, and it's moving at a velocity v. Okay, for me on this office chair was maybe like a few miles per hour. If you cycle back home, maybe if you really, really push it hard, you can go like 20 miles per hour. If you drive 65 miles per hour, or maybe a bit faster, depending on where you go. So you will get distance that the train covers while this baseball is traveling, which is just velocity times the travel time. Okay, and then the only thing that we have to figure out, what is actually the distance that the baseball really moved? Sort of this side of the triangle here. And this thing is just given if the baseball light at the speed of light times the time it takes for the baseball to go up and down. And that's all there is. Okay, so now you can see we have a triangle. We have our 2,000-year-old math. We just plug this in. Okay, there's relativity for you. Or maybe it will not look really like relativity yet. What you can do, if you kind of fudge this around a bit, you can transform this in an expression that looks like that. Looks complicated, right? There's some weird square root that maybe we don't like, v squared over c squared. What does that actually mean? Now, this expression contains one of the fundamental insights that relativity has. I'm going to show you visually what this expression means. We don't really have to use it otherwise. So let's imagine there's a horse grazing here. And we see the horse from the train, and we wonder what this horse look like. So this complicated math, so this is Einstein plus Pythagoras, is telling us we multiply by this factor. So if you want to check, you can actually check me, because I got this number wrong. I had to do it 3 times. This is really hard for me. So you can take your calculator on your phone, you can plug this in, and you just type square root 1 minus 0.98 squared. If you type this in, the number that will pop out is 0.2. And you're free to check me if you want. It's a very nice exercise. Okay, so you plug this in, 0.2. What happens with the horse if I multiply it by 0.2? Any ideas? If I do that, horse times 0.2. Okay, that's what happens. Get a shorter horse. And so one of the very, very key features about relativity now is if you move really fast, if I was moving here on this chair, everything looked the same. I mean, I didn't shrink. And that's because my velocity compared to the speed of light is basically 0. And then I get just stretched by something that's 0.9999999, and that's basically me. So you wouldn't notice any difference. But the main important fact is if you start to travel near the speed of light, these effects become important. And what you would actually see is not this horse, but you see the compressed horse. And so while we here at rest would see the horse just grazing, if you look outside of the train through the window, you see this heavily distorted horse. And the faster you go, the more the horse shrinks. If you move almost at the speed of light, the horse would merely just, be maybe this thin. Okay? And with this in mind, we're going to see a nice cartoonish example what it would actually look like if now we were in some city or we would, sit on a spaceship. What would we see? Because that means that our perception will be fundamentally changed if we travel at those speeds. Okay, here's an example. This is in the city of Ghent in Belgium. There's a nice canal. You can see the boats. You can see these nice old houses. And this is with us just basically sitting there, nothing happens. Now imagine I do the same thing. I boost to 80% of the speed of light. So I go really, really, really fast. What would happen with this picture if I do that? Yeah? It will become more blurry, that's right. You even know more than me because that's something I haven't told you about yet. Yes, it will become more blurry. That's great. Anything else? Yeah, it will shrink. Okay, this is what we would see. Okay, and so what we would see is if you look at the boat shrinks, the houses shrink. There's even a part of the house that we're not even seeing here. It sort of shrinks into the picture. So our whole perception changes. And then there's something that here suddenly it gets very bright, so it gets blurry. There's another effect that's going on. If you move very hard at the speed of light, some parts of space expand, some contract. And so the light sort of gets brighter and brighter, and things towards the motion where you travel become more blurry, which is an effect that we don't fully incorporate here. But you're correct. That's exactly what you would expect. Okay. And with this in mind, what we can do now, we can actually ask, imagine we sit in a space shuttle. We're not yet at the warp drive. Remember Star Trek? Who's watched that? Okay, great. Originally in Star Trek, they started inventing beaming because it was cheaper for filming reasons, right? You don't have to do all of these exterior scenes with a little shuttlecraft going around. But if you were in the shuttlecraft, when they showed this was usually not going at the speed of light. It was going below that. And so what I want to show you first before we get to the warp drive is what would it look like if a shuttlecraft would come fly by, maybe at like 0.5 the speed of light or 0.2. So this is a nice animation that was done by a graduate student in Germany. So this is a German town. Don't worry about the German gibberish there. That's not important. What is important is so this spacecraft over there, which you can see if you see the number on it, 1701. That's from the Enterprise. And so what they did is they put a little shuttle that will fly from left to right, okay, through here. And then we can see on the left what we would see when the shuttlecraft flies by. And on the right, we would see what you'd see in the cockpit. Okay, so what would your perception be if you travel at 25% the speed of light? And we've already seen something must get compressed, but 25% of the speed of light is not really fast. So the effect will be subtle. And then we suddenly, slowly kind of ramp it up until we go to the speed of light. Okay, so this is kind of the first of 3 videos just to get us some feeling for how this works. Here's the little shuttlecraft. You can also see the numbering there. 1701 just goes all the way through. And here you're just traveling very, very slowly towards this market square. And just keep it running for a bit. And just so you get a feeling for what you expect to see, what happens with those beams, those pillars there on the right, how they would bend as we accelerate later on, or just what the whole setting is. And then we're going to see 2 more versions of this, one that's at 75% of the speed of light, and the other one that's, I think, at 99% of the speed of light. We can see how our perception would really change as we travel at those speeds. Okay, so this is really, really slow. It's kind of slow motion, right? Of course, if you travel at the speed of light, you'd already be gone. So here it is, some of the assumption that the speed of light would be more like 30 miles an hour. So, okay, So this is kind of the first of those three. Everything is really slow. Nothing really changes. This looks like you're driving on the freeway. Right? Not much happened. Okay, so let's speed it up a bit. So this is at 75% the speed of light. And see what that would look like. It's already going faster. And now I want you to focus on those beams over here. Okay? You should carefully look because they won't remain straight as you pass by. The effect is still subtle. It will be more pronounced when we go faster, but it's already there. So you already see the sort of short contraction. You can also see it here because now you can see more of the shuttlecraft than the side because the side is shrinking away. We're going to see that again if we speed up a little bit. Okay, so are you ready for almost light speed? Yeah, okay, 99%. Here you go. Watch carefully on the right. We can play it again. Right? Now you can see that everything in the direction that you move is contracted. The other dimension is unchanged. Things seem to bend forward. It's a very, very weird feeling. The first time I saw this, I thought it should be the other way around. It's really counterintuitive. There's nothing, I think, that otherwise that you can experience this way. Okay, maybe let me just play it again, just so that we can see this once more. So we accelerate. Now we travel almost at the speed of light. Really, things get distorted, things bend. And this is what we would see. Okay, so our perception would fundamentally change if we travel at those speeds. And there's even more, as we already heard about blurriness. If we do this for real, there are two effects that we're missing out. One is the blurriness at the center, just because things should get brighter. The other one is that fundamentally light itself also has a length. Okay, if you talk about, maybe you've heard about ultraviolet light, infrared light, that's the wavelength of light. So there's a fundamental, very, very tiny length scale associated with light itself. And that one will also contract, which means that if we would put all the physics in that would go on, also the colors would change. It's really a very, very strange perception that happens. But the problem is, it's so strange, it would confuse us, so we didn't put it. Okay. But I think the main effect is really sort of this contraction in action that we can see. Okay, so with all of that said, the obvious question for interstellar travel is, okay, we figured this out. Why don't we just go at the speed of light? 670 million miles per hour is super fast. Isn't that enough? All right, let's look a bit at the cosmic neighborhood. Where are the places that we would want to visit? So I highlighted some here. So this is roughly where we are. This is the Milky Way. This is our galaxy. There's a central black hole. And since a few years ago, we actually know roughly what it looks like. I hope many of you have seen this image of the Event Horizon Telescope, where they used radio dishes, effectively using a trick to make it as big as the size of the entire Earth. So this is the best we can do at the moment without going to space. And you can highlight in the radio emission all the hot gas that orbits around the black hole. So at the center, the depletion, where it's a bit darker, this is where the black hole is. And then there's gas around that shines, and this is what you see. So it would be really cool to see close up. So maybe that's something we would want to visit. Or if you want to visit our neighboring galaxy, that's about 2.5 million light years away, meaning if you travel at the speed of light, you have to wait for 2.5 million light years. And here, center of the galaxy is 26,000 light years. Okay, closest solar system, which is Proxima Centauri, it's like our own sun, but just the nearest one close by, outside of our solar system. That one would take 4 years to get at light speed. So those distances are so vast and so large that even traveling at these extreme speeds that Einstein predicted, we can't reach them. So there needs to be something else. This is why sci-fi invented things like wormholes and the warp drive. And we're going to see how they would get around this. But fundamentally, we have to do something in order to get there. Okay, so the problem then is, if Einstein says 670 million miles per hour, that's it, what can we do? Is that it? Can we go a little bit faster than this? Is there a way around? And so the solutions, I tried hard to come up with an analogy, and I think I have one. The ways around this is sort of on the level of the following image, which is taken somewhere from downtown LA. When you go back, or somewhere in the next days, you might pass by an intersection just like this. There's a gas station to your right. There's a traffic light here, and it's red, and it won't change to green. You wait there, and you're like, okay, I really don't want to wait there forever. So what can you do if there's a no turn on red sign? You just wait, or do you do something else? Through the gas station, yes. So you could, I'm not sure it's legal, but in principle, you could think, maybe there's a gas station there. You just go on the gas station saying, maybe I want to fuel up, then you last minute change your mind, and then you just exit the other side, okay? This is nothing that if you take your driver's test or you learn how to drive from the DMV manual, that's not in there. They won't teach you this, but it's not strictly impossible either, right? And so the solutions that sci-fi has invented are all of this kind. It's basically, in principle, not allowed, but in practice, you can somehow find a backdoor way through it anyway. And this is how the warp drive works, and this is also how wormholes work. Okay? And the reason this works in physics is there is no gas station, but there's curved space and time. So one of the other predictions of Einstein is, this was his first prediction, then he did basically what ChatGPT thinks I do, but for 10 years, and thought about how to do this more generally. How can you do this not just for motion, but for gravity itself? How can you model gravity within this framework? And he figured out that space and time need to be treated on an equal footing. This is something very strange, right? It basically means, one implications of this is that the Earth and the moon kind of make a dent in the fabric of space-time, and this way you explain gravity. And the crazy thing about it is, because you can do this, because space is more complicated than just a flat space that we experience every day, you can find ways around, just like the gas station. So the question is, what's the cosmic gas station for our problem? And so one way that people have suggested within this kind of spirit is a wormhole, which is like a hidden back door. You just open it up and boom, suddenly you're somewhere else. It's like Alice in Wonderland. Okay, and you can see multiple examples that have been invoked. There's like Stargate, where you can travel to a different planet. It's like one of these old phones. You just dial the right number and it gets you there. Or there's one also in the Star Trek realm for Deep Space Nine, which gets you to a different quadrant of the universe. Or our very own Kip Thorne proposed at Interstellar. You should really watch that movie if you haven't. That there might be a wormhole that takes you to some gargantuan black hole. Okay, and this is what it would look like in a more realistic setting. Okay, and if you want to learn more about wormholes, there's a wonderful stargazing lecture. In fact, the 100th stargazing lecture Kip gave, it's on YouTube, where you learn all about it, how it works, how you keep it open. There's one thing personally that I have about wormholes, and this is in practice, this is great, but it comes at a catch. The question is, do you really want to travel to a wormhole? I mean, this one looks nice, and that one looks nice, and that one looks okay-ish. But I happen to have a collaborator in Canada who's recently, just last year, did the first simulation of what it would actually look like, or not look like, what would happen if you travel through a wormhole. It's a computer simulation taking into account Einstein's equations, taking into account basically what a kitchen sink would do. I'm going to show you this movie, and maybe then you agree with me that that might be a dangerous thing to do. Okay, so this is what it looks like, almost like a kitchen sink. You have some stuff over there. Think about this being water. Then you just pour it down a drain, and you wonder what comes out at the other end. Okay, this is the wormhole where you want to go through. So I'm going to play that animation. This is what it does. You pour stuff in at the top, goes all the way down, and then it comes out. But now you can see there, it's almost clogged up. There's something happening there. It's very turbulent. It's like if you sit on an airplane and they say, oh yeah, turbulence is coming. Like this is that stuff on steroids. Okay, so if you want to fly through there, it's not only going to be super, super hot and you're going to be boiled in there, but also you're going to be shaken around like crazy. So I don't think it's something you won't want to do. And so this is really something why, maybe we need something else than the wormhole. Though the wormhole is still great, so you should watch Kip's talk. I think this is nice, but this is what it would actually look like. Okay, so the question then is, if wormholes might be dangerous, what other options are there? So this is taken from Star Trek, The Next Generation from the 90s. There you have Data and Captain Picard, and they want to travel to some new solar system. It's a big question in astronomy right now, if there are systems like our solar system, if you want to visit another Earth. I think we can't hear the audio because otherwise our IT breaks, but they basically say, let's go to the Viridian system. Something happens now, and the spaceship accelerates away. And this is the warp drive in action. And the final thing we need to do now is to say, how does the warp drive actually work? And this gets us to the main part of tonight. And so if you look at Star Trek itself, what you find is they give you some clues of what they think a warp drive would do. And then what we're going to do together is to analyze if it's physical, using a very nice hands-on demo. So I'm going to show that as well. And so if you look watch the series, there's many of them, watch the movies, they'll tell you something like a warp field. They even show this in one of the episodes there on the right. And you can see there's some field lines, is what we would call them. And they get somewhat compressed at the front and expanded at the back. Okay, so there's some bubble that's established around a spaceship, and that kind of lets, all of the laws of Einstein go out of the window. You can travel how fast or ever fast you want. You can see it here. You also get some nice effect with the length, but here length suddenly expands. It doesn't contract. So it's exactly the opposite of what Einstein would say. And the question is, how does that fit together? And so the nice thing for me is, as Cameron said, we do computer simulations, and you'll see some of our students later on in the panel. Actually, somebody doing Einstein simulations on a computer as a grad student, a Mexican astrophysicist called Miguel Alcubierre, figured out what a real warp bubble would look like. So this is actually a real warp field. If you believe Einstein's equations, it's compatible with Einstein. We're going to see how that works. Okay, so there's real physics to this. In some sense, there's some catch about it, but there's real physics to it. You can actually build something like a warp drive, make it consistent with Einstein, and ask how fast can you travel. This is more reality than it is fiction. Building this thing in practice, as we'll see, will most be impossible. Okay, because Einstein was complicated, and we said we don't want to go more complicated than Pythagoras. We can't really go through his solution in detail, but the good thing is we can do a hands-on demo and basically show you here what the physics behind the warp drive is in a simple experiment, which we're going to do now. And for that, I brought something, namely my own space-time, which you see right here. Okay, this is my space-time. I can turn it around, I can spin it around. Maybe I could even wear it if I want to. That would be great. But what I can do with it, I can warp it. I can literally warp it with my hands, and so I can show you how the warp drive works. So we're quickly setting that up, and then we're getting all ready to see how that works. Okay. Right. Okay, so I put my space-time here. And remember, space is not flat. And you can see that space is not flat because I can do something like this. Okay, I can just, move it around. I need, of course, something to visit. And so I thought I'd bring you this. This is a black hole. This is an actual black hole. It's a 3D printing of two black holes that are just about to collide. They were simulated solving all of Einstein's equations using one of our very advanced computer simulations here. It's a nice print that one of our undergrad students made last summer. And I'm going to put that here. So this is what we wanted to visit. Okay, so I need somebody to visit it, and so I brought Uhura, just from Star Trek, okay? And so Uhura is here, all right? And Uhura needs to get to the black hole. The problem is there's no way she can move there because that takes forever. So what can you do? If you had a wormhole, I was thinking of demonstrating it, but there's a catch to this. If I were to show you what a wormhole is, it's basically this. I take the space-time, and now I would need to take a knife and stab the rug because I need to poke a hole through for you to go through. It's also destructive. It's not only dangerous. So I won't do that. Rather, what I will do is I will show how the warp drive would do it. And the main idea is, imagine now if I could take space, right, which is very, very far, could just bend that somehow together, just like this. Okay. And then suddenly, if I'm here, the black hole is very close, right? I've just compressed space. And then I can just move over, and I'm at the black hole. And then, of course, I don't want to leave space compressed, so all I have to do at the end is I just unfold it again. Suddenly, space looks like before. Okay. So the fundamental idea of the warp drive is you compress space ahead, space and time, you compress it, you expand it at the end, and suddenly you have moved much, much faster than the speed of light. And we're going to see some animations back on the slides of how this works. So let me show it once more with the rug. So I take the rug. Okay, this is where I am. I want to get over here. I just compress it totally like this. Okay, so I can then move over. And this takes only a very, very short amount of time because I can compress it how much I want. Right? All I have to do afterwards, I have to clean up the mess and just pull this out again. And this is the fundamental idea behind the warp drive. Okay. All right, so let's get back. So we again have to do a technical commercial break just to switch back for people on Zoom. Wait, I want to do that first. I want to do that. And I want to reshare. Okay. Okay, great. So what we've just seen was basically this is our rock, this is Uhura. There, X marks the spot. This is where the black hole is, where we want to go. But the distance is very long. So what we want to do is we want to compress space and time, just like the warp drive would do. We just squeeze it together. And then we clean up our mess afterwards. So we have to expand after we've moved. Okay, so we shorten this distance here just by compressing the rock together. Okay, so this is really what the warp drive does. Take space and time, compress it together, pull it apart again. Okay. And the nice thing is, the more I squeeze it, the shorter this distance gets. And then you get a factor C, and we might be free to call that the warp factor. Okay. And so if you know from Star Trek, there's something warp 1, warp 2, warp 3, that's basically just telling you how much this compression is, just that they use an exponential scale. Okay, so you compress space together and you expand it again. And the nice thing is you can make this arbitrarily small. So even if locally on sort of this yellow plane, you travel below the speed of light, you're fine. So it's basically a way, just like with the gas station, where you go at regular speeds to the gas station, but you're still there quicker than waiting for the red light to change. Okay, this is really the same kind of philosophical concept. And there's another thing about it, if we have a better analogy of how you could do this, because it's not just that you can warp space and time. If, and I hope we don't get this, but if you were to feel an earthquake does the very same thing with the Earth itself. You can listen to it just like you can listen to me when I speak, which is a sound wave. So you see the molecules, or you hear the molecules as I kind of excite them, they propagate over to you, they vibrate in your eardrum. The same thing happens with seismic waves. They also propagate, they vibrate. You can't hear them with your ear. You can feel them as the ground shakes, but there's special devices, the seismograph here, that can record it, just like you can record audio. And if you see how the earthquake, how the wave travels to the ground, you can see here in this animation, that's just like the warp drive. So you have a front ahead that compresses the Earth, this medium will come again here, compresses, and then in the back it expands again. This is what the propagation of a warp field would look like in reality, just that you don't compress the Earth, but you compress space and time periodically. Okay, so there is some actual science to this, if you so want. And then what you can do is, you can basically go and you can make this distance to a planet arbitrarily short. There's one catch: you don't want to switch on the warp drive for reasons I should tell you in a second next to Earth. You really don't want to do that, because if you take Earth and you squeeze it, that's a bad idea for us on there, right? So you have to travel safely a distance s, kind of a safety zone at regular speeds. Then you can switch this on. You travel again for your destination. You don't want to switch it off there. That's also not good. So you want to kind of, just travel this distance d, and that's really the distance that you can boost with your warp factor. And then you're only limited in practice how large the safety zone is. Okay, sounds great, right? So we're ready for interstellar travel. So why can't we really go there? Okay. So the main reason, this is the problem, and this has nothing to do with Einstein. What the problem is, the problem has to do with quantum physics. Maybe some of you have heard some question that always comes up, that Einstein is not compatible with the quantum realm for very interesting reasons. And the same thing applies here as well. We had to cheat somewhere, much like we had to cheat at the gas station, right? You have to violate something. There's no way you can just, take a shortcut and not do something wrong. And the same thing happens with this warp drive as well. In order to keep the warp bubble open, you need something that's called negative energy. That's a really strange thing, because it doesn't exist in our daily life experience, okay? Or in most things on the planet, except one exception I'm going to show you. So the problem is, you need something very, very exotic that will keep the warp bubble from collapsing in on itself. So the challenge with that is, you really run into issues at quantum mechanics, because the only way you could generate this energy would be from quantum fluctuations of space-time itself. It's a very nice thing for the discussion session. There's an effect, it's called the Casimir effect. It's a very bizarre thing where we basically say you put two plates in empty space and suddenly they attract themselves. It's a quantum mechanical force that builds up. And it builds up because space fluctuations around sort of zero are always positive and negative. And if you can just the negative ones, then you get negative energy. But that will put so strong constraints on this warp drive in practice that building it, I think, is a challenge for future generations. And the main reason is, if you compute what is the energy required to fuel this, your gas station that we saw, the fuel you get there, that won't be enough. Okay, you need more than, let's say, 12 gallons or so for this thing. So the big challenge is people have actually calculated this. So it's very interesting. After Miguel Alcubierre in 1997 wrote down the solution, several people worked out scientifically what the required energy is that you would have to fuel this. And there are two options. Option one, we sacrifice one of our planets. So you should go and look before it's gone, because you have to sacrifice the entire planet to even get the simplest version working. And then if you want to build a big spaceship of kilometer size, well, we have to sacrifice our entire universe. So maybe that's not feasible. Okay. So the real challenge is, how do you get the energetics worked out? And this is something I think that will keep future generations busy. But while you go and you look at Jupiter, I think about this. That's the thing you would have to give up. And if you want to go again, you have to sacrifice the next planet. So Mars is next. Okay. And finally, this is an interesting question, I think, especially for us at Caltech, because one thing that for those of you who come regularly, you've heard maybe already, Caltech is very famous for pushing the frontier of listening to waves in space-time itself, to gravitational waves. If black holes collide in the universe, they have a chirp, they sing, and we can listen to this with detectors such as this one, where we can tell you more about in the Q&A session, because I don't want to keep you from watching the planets. But one of the interesting things that happened last year is that people using computer simulations computed, could you actually listen to a warp drive? Because a warp drive should also emit gravitational waves. We saw it also wiggles space and time. Is this something that we could actually detect? Or you could be more provocative and say, can we figure out if aliens visit us or so? So the answer to this is, we can't unless the space-time explodes. So if for whatever reason the space-time would blow up, just like you see in some Star Trek episodes when they have a warp core breach, then you can hear it, and this is what the gravitational wave signal would look like. It will be so high frequency, you can't see it with this detector, but maybe in the future you can, although there's some intrinsic challenges. But in principle, we can even listen to the warp drive if it fails. Okay, with that, I hope I've given you some motivation or some curiosity to think more when next time you see on TV or in movies, interstellar travel, Star Trek, Star Wars, Stargate, or even when you go outside and you watch the universe with your own eyes. Thank you.
We can take a handful of questions for our speaker before we break for the stargazing and the panel Q&A. Do we have any questions? Yes.
Thank you for this. So let's say you wanted to travel to a point that's 1 million miles away from where you are, where you're starting, and you warp space in this fashion.
Yeah.
So that effectively it's 150,000 miles of distance that you travel because you've compressed it by 850,000 miles. Are you really traveling faster than the speed of light? I mean, this is a specific example, and you do it in a second, right? In this specific example, you move 150,000 miles in a second. That's below the speed of light. So is it like a fiction or a cheat to say you're traveling faster, or is it actually possible to warp in such a way that you actually would be moving at distances faster than the speed of light?
The interesting thing is, if you think back on the example with me on the office chair, it will actually depend on who's asking. So for me on the spaceship, it will not feel I'm traveling very fast. It will feel just like you sit in a car. You might not notice if you go at constant speed, or you sit in a plane. You might not even know you're in the air. But if you sit here and you actually take the time of you going there and going back, and you just compute what's the speed, you would figure out the apparent speed you measure is larger than the speed of light.
Additional questions? Yeah.
Thank you very much. So what would happen with time dilation? Would there be any kind of time dilation in a warp drive?
That's a great question. So it's not just that we said that space and time have to be treated on the same footing. So the question is, if length shrinks, also time has to shrink. So there's something called time dilation that's going on. And the answer is yes, that's going on as well. And that's actually the main reason why we couldn't in practice just ask the question, if we travel very near the speed of light, our time goes very, very slowly. So in principle, for us in the spacecraft, it wouldn't matter if we travel 2.5 million light years. We just have to travel fast enough to not notice it. The problem in practice is if you want to get back, for people that are not traveling at the speed of light, the time would still move fast. So everybody would be long dead by the time we get back. So the problem is really time dilation happens, but if we don't have something like the warp drive, there's no way we can go back otherwise.
Other questions?
What's like the current technology? How fast can human travel currently? Is there any like machine or anything like that people are working on?
Oh, you mean how fast can we travel at the moment, just technically? That's a good question. I think we can go at Mach of a few, Mach 3 or so with one of the fast fighter planes.
I think it depends on the environment. I think the fastest, I remember learning recently that the fastest human-made object that we've gotten to build is the Parker Solar Probe, the instrument that's flying and quote unquote touching the sun, if you've seen this in the news, but it's achieving these speeds because it's falling into the gravitational well of the sun. So as it gets really close to the sun, it I don't know, I think it's like 0.0001 C or something, the speed of light. So it's fast, but it's.
But then we are not on board.
But we're not on board.
We're not on board.
That's right.
Yeah.
So in Interstellar, I know that when Kip Thorne kind of helped with the script, he brought up an interesting idea of traveling through higher dimensions. And I know the physicist Lisa Randall has talked about that too. If theoretically, if there was a higher dimension, you could travel and it wouldn't cause the same issues that you mentioned. Just was wondering if you could talk about that.
That's right. So basically the idea is in those theories, you basically assume, let's say we have more than just space and time, so more than 4 dimensions. I can show you what that dimension look like. So in this, what's called the Randall-Sundrum universe, this is what Lisa Randall invented. You basically take space and you curl it up. Okay, so you have another dimension that's just rolled up really, really tightly, much more than I can do now, basically to very, very tiny scales. And then yes, you could think about maybe this other dimension connects you just like a wormhole would do, and then you just travel basically through the rug in this way. That's right. That would be another way beyond even going beyond Einstein, whereas the warp drive is still within Einstein itself. But yeah, that's a good point. That might be possible as well.
Hi, I had a question about the video of the shuttlecraft traveling. It looked in the video where the shuttlecraft was moving almost at the speed of light at 0.99. It almost appeared at the very beginning as though it was in reverse. It
was accelerating.
But I remember you said it was accelerating, but it appered like it was traveling in reverse. Is that just an effect of you trying to visualize the whole process?
I think it's just a visualization, because I think, okay, so in part you're accelerating, but in part you're also adjusting the camera, because once you have this contraction, stuff will move out of your screen. So I think it's both for visuals, just so that you see the same visual area plus the acceleration effect. Yeah.
Can I ask a?
Yeah, sure.
Okay. You also mentioned when a vehicle would travel with the warp drive, a kind of scrunching of the space-time in front and then an unscrunching behind it. Is that a function of the engine itself, or is
that's right? That's how powerful your engine is. The more powerful, the more you crunch, the more you squeeze. Yeah.
Okay. Thank you.
And so that basically was the point about if you only sacrifice Jupiter, you might not go as fast.
I have a question related to the previous question. So particularly for your 99%, the speed of light, you'll see that the left one takes quite a bit longer. The left movie takes a lot longer to make the transition through compared to the right. Is that a time dilation effect? Like it zooms all the way through on the right side, whereas on the left side, it's still just chonking along there? Is that because the videos are out of sync?
I think the videos are fundamentally out of sync. For the time dilation, it would go the other way around.
That's what okay.
So that would be the point. So if you were time dilated, then on the right you would barely move, and on the left you would just fly.
Okay, so this is just
that's a good point.
A technical difficulty. They're out of sync with each other. Okay, just wanted to make sure. One last question for this before we go to our panel.
I've always just been curious. I don't understand, if we had a laser shooting into space and then there's a spaceship flying at near the speed of light directly across from it, their perception is that it's still moving away from them at the speed of light. Is that because it's dilating? You're inside of the warp bubble of the speed of light. I've never understood that.
Oh, you mean can the beam actually hit the spaceship?
No, I'm saying if you're riding next to a beam moving at the speed of
Yeah.
light and you're going 99% the
Yeah.
speed of light,
Yeah.
but you're still seeing it move away from you at the
Yeah.
complete speed of light, as opposed to if you're running next to someone at
This is the original observation that pointed Einstein to think that the speed of light is the upper limit, because that implies that regardless of how you move relative to light, it always moves at the speed of light. And that's the thing that even 100 years ago, they could figure out experimentally. They were trying to see if you take the motion of the Earth around the sun, which is also a velocity, right? If you add that to the speed of light, does the speed of light actually go faster or slower? And the answer is no. So that's a very, very curious fact. And because of that, there's relativity. So that's really what you're asking is, it's the mere definition of relativity itself.
On that note, let's thank our speaker. Okay, so for those of you who want to stick around for the next hour or so, we're going to have a Q&A panel up here that'll get started in about 5 minutes. Any questions you didn't just get asked, you can ask our panel. Our speaker will be on it, as well as a few other members of the department. We have telescopes set up outside, again, looking at various planetary objects, as well as some deep sky objects in our Milky Way galaxy. And you can go back and forth between the two if you want. So you could go check out telescopes, come back in, stick around, whichever. So our next event, Astronomy on Tap, is postponed from this coming Monday to the week after, February 3rd. And that'll be in Old Town Pasadena. And our next one of these is on Valentine's Day, February 14th. Thanks for coming. And maybe you'll stick around for the panel. We'll be started with that in 5 minutes.
We did one on time travel.
Great.
Sold out. I mean, people loved it, and we got into philosophical stuff with eternalism, with presentism, philosophy, and everything as well. I know that he has to be in Greece during this Comic-Con, but if you're interested, we'd love to have you on a panel as well.
Sure, absolutely.
San Diego Comic-Con. I'll reach out to you.
That would be great. Yeah.
And it's I told Cameron too, but it's in the last week of July.
Okay, yeah, that would be great.
Yeah, the panels do fill up, and it's fun. Yeah, and we talk about theoretical stuff like this too, and it's kind of fun.
Yeah, absolutely. Thank you so much.
Yeah, my name is Nikhil, by the way.
Yeah, Elias, hey.
Yes, I'll reach out to you.
Yeah, great. Thank you.
You mentioned
Yeah.
energy to fold space.
Yeah.
Do we have an idea of how to actually fold space, even if we have the energy to do it?
So if you had the energy to do it, the main thing is you have to separate the positive energy from the negative energy. And once you put that there, I think space will self-fold. It's the same for the wormhole. In order to keep the wormhole open at its core, you also need to have negative energy. So if you have a way of separating those out, and you just pile enough up in one location, I think then you start doing this. The main issue with the warp drive is there's a fundamental problem, at least with the Alcubierre drive solution, in terms of controlling where it's going. Because fundamentally, the helm of the ship is disconnected causally from the ship itself. So you would need something go ahead and then tell you where you would drive to.
Awesome. Thank you.
Yeah.
My name is Will.
Hey, nice to meet you.
Nice to meet you. I have some questions.
Mhm.
First, what happens to the space that's in front of warp drive? Like if I'm a person in the path of it, am I just gonna get squeezed?
You get squeezed.
So you get harmed basically, or the matter gets compressed and destroyed or whatever?
It does not get compressed. I think the big question is sort of the good thing about space is the density is very low. So there you can just avoid hitting people. If you were to launch this here, I think the biggest problem is that you have the negative energy. And so that would react with you. We would burn up basically. Yeah. Uh-huh. Yeah. Yeah. Oh yeah, that's right. That's right. It looks like it's going around. Yeah. Mm-hmm. 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 I think space and time is sort of going around, right? But like you still get if you go around, it's like you squeeze and then you go around, or you just end in the negative energy. So you have to be a bit careful of where you are. But yeah, yeah.
If you have any answer? Like, how do you even like? I guess how does something compress space? Like, where do you even begin to?
It's like.
Compress.
No, you have very special matter, like exotic matter that we don't have, right? And then what the matter effectively does with space, it pulls. That's what it's doing. It's a very, very exotic matter solution. So if you actually watch the series, they say, oh, you have antimatter, but antimatter itself is not enough. You need exotic negative energy density matter from quantum fluctuations. If you can create that, that will just pull space-time, just like a rubber band, just pull it by itself. Yeah. That's right. That's right. Yeah, it is.
If a gravitational wave will be strong enough, how do you combine it? Can you combine it with a warp drive? Use it to like.
Oh, you mean just give you a push? Yeah, for sure. So the interesting thing, you could in principle, you can show that if you have gravitational waves that collide, they can contain so much energy that you locally form a black hole. So that's possible. It's not gravitational waves that naturally form from colliding black holes, but you could set something like this up. I mean, if by then people figure out how to build a warp drive, they can do that too. Well, thank you. Thanks so much for coming. Yeah. All right. Great. Okay, cool. Right.
Go ahead and take a seat.
Okay.
All right. Thanks for sticking around, everybody. We'll get started with our Q&A panel. What I'll have everyone do is introduce themselves and the sort of science that they work on, and then we'll start taking questions both from you as well as our online YouTube audience. They can ask questions remotely. So as I mentioned, I'm Cameron Hummels. I'm a research scientist here and run the public education program. My research is primarily about galaxies and the atmospheres kind of around galaxies. It turns out, yeah, galaxies have atmospheres kind of like our planets do as well, of lower density material. It's called the circumgalactic medium. It's harder to see, much like our atmosphere is harder to see than, you know, the solid and liquid stuff here on the surface. But it turns out that it plays a major role in how stuff gets into and gets out of our galaxy. And we're trying to, I'm doing computational models of that to try and better understand how galaxies form and evolve.
All right. You just heard me talk for quite a while. Yeah. What I do when I don't think about warp drives is I look at, recently we looked at what happens with colliding black holes and exotic stars. We look at matter on black holes, gravitational waves. We have Sarah those events. She can tell you more about that.
Right. So I'm a graduate student here, and for my research, I work to build code that we use to simulate black hole collisions. And this is a very difficult problem because set of equations to do that. And there are a lot of moving parts that you have to make sure are working perfectly to get this to work. People like this. And I work with a lot of people, including Elias, and collaborate.
Sarah, we can make all of those movies. Compute really the kind of noise or the sound that space makes itself. That's really what Sarah does. Quite amazing work.
Everyone,
with the holes about something called seismology, astroseismology. This is sort of like studying earthquakes, but instead of on the Earth, I study them on stars, right? And the reason why you might like to do this is because if you think about it, you know, as you see the folks outside, the vast majority of the information we get about space comes from light. And unfortunately, for someone who likes stars a lot, you can't really see through a star. So it's really hard to learn about the insides of stars. But you can see a trick where it turns out things like sound waves actually go right through a star. And so if you measure the sound waves on a star, you can actually learn about the deep interiors of those stars.
Is it
right, Nicholas, if I would say that you should code the Morse code in stars?
We can put it like that. Yeah, that sounds really nice. Yeah. We ring the bell of the star and then we hear what it sounds like inside. Yeah. And so I basically do the math and I run the code which figures out how we can measure things like the internal structures of stars or the strong magnetic fields that they might harbor in their cores just by listening to them. So that's what I do.
Okay, questions from all of you guys. Do you have additional questions either on the content of the presentation or on something that we raised or whatever? And I feel like this mic is not working well, so I'm going to use it. Hopefully this one.
Yeah, thank you. So I still want to ask about the faster than light part of the talk. So I guess we talked about so for the person who is actually on the warp drive, it wouldn't appear to be faster than light. So I guess my question is for a stationary, well, quote unquote, observer. I guess in this time you have a space time that is that. So the metric is evolving across time. So I guess how do you define a distance globally for even for the stationary observer?
Well, how do you define a distance that you travel? Yeah. So you can still, it gets a bit complicated if we go too far away from where we are right now, because also the universe is expanding on large scales. But if we are very, very close, right, there is something you can always define a local reference frame effectively as the time. Imagine we take some of those little shuttles that travel below the speed of light, right? I could just, have that go on. It would take very long, but I can define an effective time that takes at a constant speed, and that would give me a distance, right? And so you always have a reference distance that is meaningful to us here on Earth, because ultimately what you care about, let's say you want to bring back some, gas from around our central black hole. Really what you care about is the time it takes for you to get there and to get back, right? So it's really the distance that matters relative to us. Whereas on the spacecraft, I mean, maybe you can go back 10 times and you don't care.
I see. Thank you.
Yeah.
Additional questions? Oh, yeah.
Thank you. So I actually want to understand a little bit more about light. So light obviously have a source, right? And then how does light choose its direction and what happens toward the end of the light, right? And is there any relationship between really time and light in terms of light being aging or fading? Does time matter to light?
It's a good question.
Yeah.
So I guess, thank you. So choosing is a bit of an interesting word, because really what the path that light takes is essentially the shortest path in space-time that it would be possible for it to take. So you can imagine you have a hill and you're pouring water down, and the water is just going to go whatever way is easiest for it to go. And that's exactly what light is doing with space-time too. That's exactly one of the consequences of Einstein's theory of general relativity, actually, is that gravity can affect the path that light travels. And so we predict some really interesting effects from this.
What happened toward the end of the light? Does it fade away eventually? Because it's trying to get from place to place, but what happened toward the end of it? It has a source, and what's the end point?
Well, the end point is whatever object is in its path that will interact with it somehow. So basically, it depends on what it runs into.
It could either break the light, right? Or it can it swallow the light? But what happened when the light breaks, it's still going somewhere, right? It's still a forever kind of thing. Okay.
I do want to say something. Actually, I want to spin this a bit. So yeah. So in a very simple picture, we kind of have a flat space-time, just like the universe is, as we kind of experience it right now. If you just shine a ray of light, as Elias and Sarah said, basically the light just goes forever. However, the universe is actually expanding. It turns out the expansion of that universe actually sort of stretches out the light, right? When you stretch out the wavelength of the light, that actually makes the light redder, right? And so I don't know if you've heard of something called the cosmic microwave background. This is basically like a sort of really like sort of low intensity hum of light that is like sort of coming at us from all directions. It's so red that it's actually invisible to us. It's in the microwaves, like the kind of microwaves in your microwave oven. And the reason why they're so red is because early in the universe, it was really hot. And so like you had a lot of blue light. And then that light, because it was stretched out by the expansion of space, was sort of in some sense kind of fading away over time. So that now that it's been stretched so much, it's this very red light. So if we sort of think about things on cosmic time, light does sort of fade away. But on sort of short times that we're used to thinking about, it basically just goes forever.
These mics are giving us problems.
Question for if you have ever read Frank Herbert Dune. I was expecting that. Okay, so instead of them jumping in their ship just by their ship, they use a portal type and they jump through the portal type. And it's, so their planet is right next to the portal. And then they just jump right through the portal, right to the other planet, which was Arrakis. So is that what would be more, I guess I should say, what would be on an idea level of what would be easier to do? The ship, just jumping, using the ship, or using the portal type? And then the other question, I'm sorry, was
yeah. Connected with another hole, and then you just go through. No, the portal is a wormhole in principle, right?
Is it a cool
wormhole? The only thing is that for the wormhole solutions, at least in the book or the movie.
And then the other question was for the coders, how long did it take to code one of your simulations?
So there's writing the code to produce the simulations, and then there's actually running the code to get the simulations in the end. And writing the code is a process that has been going on for decades and is a huge effort, and we're still working on it. So I'm glad that's the case because I have a job here. Running the simulations, it varies a lot and it depends on what you want to run. So if you want to run a really simple collision between two relatively light black holes and not for a very long time, then it will take on the order of days. But we also have some simulations that will take on the order of weeks or months. So we have to be really resourceful about what we choose to run. And we also have to be absolutely sure that our code is right.
So like a type of supercomputer or super data center here for that?
We do have computing clusters that we run our code on. There are very few things that are on the scale that you would be able to run on a laptop or a personal computer.
I will say, and this is something that I don't personally work on, but these folks, and especially Elias, work on, is it turns out, so if any of you like play video games and are like really into like maximizing the efficiency of your setup, there are these things called GPUs, which are, you basically can like sort of put them into your computer and then they kind of help draw the graphics in your video games and things like this. But it turns out that fundamentally what they do is like very simple operations super efficiently. And so what folks like Elias and other people who do very sort of high performance computing do in physics is they basically like sort of chain a bunch of GPUs together and then have them like tackle the universe's hardest computational problems. And so, yeah, it really is required to be resourceful to push the boundary. Another thing, I just want to emphasize this, I think Sarah basically mentioned this, but you know, these are like really typically like the writing of codes that are used to do research, to solve research problems are like not just things that one writes by oneself usually, Oftentimes it requires the effort of many, many, many people over many years. Yeah.
One interesting point to this, the first numerical simulation that worked of a binary black hole collision, which was done here at Caltech about 20 years ago. Nowadays, you can actually run this on your iPhone if you want. So there's a software, it's called Black Hole at Homes, you can do it. The problem is, I think it's no longer supported because when they tried it out, the phone overheated. It's not supposed to cool that much. So it's dangerous. But in principle, in terms of computational time, the easiest thing you can do on the phone. But if you really want something that allows you to interpret the signals that LIGO is receiving, so really the sound it's hearing from the colliding black holes, that really, as Sarah said, takes months to compute. Because there the question is, maybe if one of the black holes isn't fully symmetric, like if the collision, there's actually one where the black hole here, the right one, is about 3 times or 4 times larger than the left one. So this is what the collision of 2 black holes look like, right? So if you want to simulate that, that will take longer. If you want to do it well enough to actually be scientifically useful, it takes even longer. And then if you want to do that in practice, you need thousands of simulations. This is why it's still an ongoing quest to basically compute large catalogs and make the data accessible for scientific community.
Yeah. Okay.
So a follow-up question.
Alternative technologies such as, namely the artificial intelligence field, do you think that could be a possibility to explore how you can apply that kind of technology to try to help accelerate the research and development for what you guys have to do for these models? Or do you think that could present like some kind of like a degree of unpredictability because you don't know, you want this model to perform this way with that result, but you don't know if the simulation from the artificial intelligence route can help you like produce that result? Is that an option that can be explored in the future?
Something we're doing already. So within the collaboration, what's happening is that if you compute 1,000 waveforms, that's not enough. So ideally, you would need a coverage of tens of thousands of those simulations. Very, very expensive. So just in terms of dollars, we basically talk about several millions of dollars that this would cost. And so what we begin to do is to actually use machine learning type algorithms to interpolate between those simulations. So basically feed them to the computer, and then it gives us some interpolation. And that's what is actually used as the best models that we have. So we're doing that already. It's a very, very good point. And I think we even have to do it more going forward.
Just to add a little bit to that, there are some problems where our solution is essentially, well, we can't solve the equation exactly or get an exact answer, but we can make a reasonable guess. And I think these kinds of problems are particularly good opportunities for like machine learning or AI or similar technologies like that, because they don't need to be perfect. And, if you've ever tried to use ChatGPT to do math, you'll see that it's not exactly the best at giving you exact answers, but it can give you something that looks like a good answer. And sometimes that is all we need.
Best approximation as to where you would like to go for the result.
Yeah, and I sort of want to philosophize a little bit, right, about the Zen of physics, right? Because it sort of sounds like a very kind of objective thing. Like I want to predict stuff, like with very, very good precision. But the way that I kind of like to think about my job is actually like it's a pretty human thing. It's like I want to take the universe and kind of understand it, right? So in some sense, like in directly achieving that goal, having something like an AI, like sort of, look at something and then directly predict what comes out is satisfying to me doing physics, just because I at some level, like there should be a human, like kind of enjoying the, understanding of what's actually going on. But at the same time, as was said before, There are some tasks which are just really complicated and just kind of would take forever if you did it correctly, but which machine learning algorithms can do not totally correctly, but approximately correctly. And sometimes that's all you need to sort of take care of the messy stuff so that you can do what you want. And so that's the way in which machine learning has potential and actually is being used.
Are you using machine learning too, Cameron?
No. The field of research in which I work in terms of computational modeling of galaxies and trying to both produce how those simulated galaxies would look if you were to observe them with a telescope and that sort of thing. There are starting to be applications of machine learning and artificial intelligence in that mode, but it's still in its kind of infancy at this point. I feel like a lot of the fields of astrophysics are kind of searching for ways to apply this new technology to them, but there haven't been too many hits thus far. One sec.
Thank you for the lecture. That was really great. I have two follow-up questions. The first is you showed us how a wormhole would work, right? And it does look like a bumpy ride. So are you saying that a warp drive would be a smoother ride?
At least once you go to warp speed, yes. The question is just how do you actually like slow down? That's an open problem. The main issue is that the helm of the warp drive is disconnected from the actual starship itself. So you need something that goes ahead. There's a name for this. It's called a Krasnikov subway, where you basically just like a hyperloop. Assume you go on a round trip. Then you would just follow through the loop, get out, and then get in again. But that's an open question still, because the question is, do you need a planet every time that you just fuel up the spaceship or not? I think those are practical challenges that would have to be solved.
And when you say to use a planet to fuel up the spaceship, theoretically, how would that happen?
We would have to disintegrate the planet completely. So we're really talking, I mean, the energy requirement that this has is beyond the energy efficiency. Like if you actually burn like fuel, the energy efficiency is very, very low, like a few percent or so. Even nuclear reactions only have like 10% or so. Here we're talking about you take the entire energy content that an object can have, like as an E equals mc squared, and then you dump that into pure energy. And that you would have to do with the entirety of Jupiter.
You really turned into a supervillain real fast there. Wait, so let's talk about this whole business. So you've got your mass of Jupiter that you have to turn into some fuel for this, but the fuel is essentially in creating the warp, the compressed space-time in front of your spacecraft and the kind of expanded space-time behind your spacecraft. But we don't have any mechanism for actually like doing that, do we?
I think somebody else asked me this earlier, and I think the first thing you would have to do, if you could actually create this amount of exotic matter, this amount of negative energy, and you just put this into one place, I think part of it would form naturally. So I would think you just have to put it in the right locations, and probably you have to do a bit more than this, right? I mean, also building an engine for a car is more complicated than just lighting fuel. But I think it would probably start out with that process fundamentally, and then you would probably need some sort of confinement of the whole process in the next phase. But I think if you could amass the energy in the first place, something will happen to space-time itself quite naturally.
Okay. Well, we need negative energy.
We need negative energy stuff, yeah. That's the first challenge. But we have a few thousand years to go, so we have some time.
Thank you. Following up, so you wouldn't need to use a planet, just something with enough energy of a planet?
That's right. That's right.
And as long as you can get the engine or ship in that location, it would work. It could be passing matter or negative energy or something like that.
Yeah.
Okay. And then also I had a follow-up about a lecture. Someone asked, I just wanted to make sure I was correct, or the statement was correct, where the person in the warp drive wouldn't experience, like, it would be normal to them, right?
That's right. The interesting thing about the solution that Miguel Alcubierre worked out is actually entirely flat inside. So inside would look like regular space. It's just that it has a bubble, right? Just like a dome around it. But inside would be perfectly normal. And the time that you travel inside of the warp bubble is roughly the same. It's like a meaningful time just as outside. There's no time dilation going on. It's just that there's a disconnect between the inside and the outside of the bubble. Like calling home while you're inside at warp speed, that might not be possible.
Exactly. So then, like you again, like you said, everybody else though, perception of that. Was it correct that you said that everyone would be long gone by then?
No. So with the warp drive, you're fine. Like the problem is more. Imagine, in principle, if you just wanted to go somewhere in a reasonable time, right? You wouldn't need the warp drive. You would just need to have to go very, very close to the speed of light, because your own time would go so slow that you would get there in a meaningful amount of time. We have actually experimental evidence for this. There's certain particles that are created in the Earth atmosphere. The name isn't important. They're called muons. But anyway, they're created and they have a half-life which is so short they would immediately decay. But still, they make it all the way down here because of that. So you can measure this. It's a nice experiment that we have our undergrads do. Now, the main thing with the warp drive is the problem is for you yourself are fine, but imagine now you want to go back, right? By the time that you get back, so much time has elapsed, nothing will be left. So if you want to go there to the black hole, let's say, and bring something back, and talk with your relatives when you get back, you better have a warp drive.
Right. And I guess that's just my final question is, how would that whole concept connect to like the idea of multiverses, like the warp drive?
That's an interesting question. So the warp drive itself does not need another dimension of space. It doesn't need quantum only in the sense that you need to sustain the warp bubble, but you could imagine that the multiverse would be something on top, but they're not related fundamentally. The warp drive is some more basic concept. Yeah.
Other questions? You had another question?
Yeah, a little bit back to what you were talking about with the humanistic aspect of AI and all that. I can see where like there can be some ethical implications as to how far we can do or what we can go beyond what we can know. So that's probably why you think that you have to take into that perspective of we can only do so much. That's why it takes time. Even with using AIs, I can see why you say there is an ethical limitation to that with that kind of perspective, right? And then the similar question asking about when you're going through the black holes, like I kind of thought in my head now, just like for human senses to try to like detect or feel what you're going through the black hole or the wormhole, it just seems like to me it's like it takes like less than milliseconds, almost like comparing to like how before you realize an atom bomb is dropped on you. You think is that kind of like there's not much reaction time to know when you are like passing through that kind of event, right? Or we just don't know like how long it'll take.
There's time dilation.
Yeah, certainly in these movies, right? It's like totally slowed down, right? Just so we kind of understand. So right. If we really showed things like exactly kind of the way that it would happen, human perception is really not tuned to match anything that happens close to the speed of light. But
there's one interesting thing. Maybe we can post the link somewhere if we have the option. There's a nice YouTube movie that a former collaborator of mine made, which is 3D compatible. So if you have like these goggles that you can put on the phone for 3D vision, you can put them on and you can experience what it would look like as you fall inside the black hole. It's the most wild thing you can imagine, because suddenly, if it's a rotating black hole and you fall in, the stars sort of spin around you and you have like the full 360-degree view. So for you yourself, it's actually like a finite amount of time. It's not that you're rushing in. It's more really strange what happens once you've crossed the event horizon, because everything is closing in on you. It's very nice. If we can post the link, then everybody can. Ziri Yunzi. Younsi. First name is Ziri.
Yeah. Oh, and I should mention, if people want to have an opportunity to look through the telescopes, they're only going to run them for another 10 minutes. So if you came and you wanted to look through the telescopes, get out there right now before they shut them down. Yeah.
Yeah. So you said when you explain like warp travel, you're like you folded the rug and then you kind of like bending it, and then you gotta like you're bending the space and then you gotta unbend it or like or
that's right.
So
that's right.
What happens if you don't bend it? You just bend it and you travel and then you leave it the way it is. Is there any like replication for that, or it has to be unbent no matter what? It has to unfold.
No, so the thing is basically, if you would keep the bend in place, you wouldn't move anymore, right? It's just like with the sound. Like you wouldn't hear me if the sound would suddenly just stop. So for you to move through space, also the bend has to move just in front of you, as the pull has to be behind you.
More questions? Yeah. And then I'll take some questions from our YouTube audience.
Thank you. So you mentioned some of the visual effects when traveling near the speed of light, the bright areas, dark areas. Light generally as well.
That's right. That's right. That's another effect that would happen. The blue shift and the redshift, depending on if you just travel or if you also have gravity acting at the same time. So this is really two very exotic things that would be going on. We didn't include it in the animation because I think it would have been too complicated just to keep them apart. But yes, that was what would happen.
Okay. There's a question from our online audience from that's specifically for Nicholas. What's the furthest star on which we can do seismology?
I mean, certainly we can do seismology on a lot of stars in our galaxy, right? So our galaxy, like sort of the main disk of it is like, maybe like some tens of kiloparsecs, I guess, maybe like, what is that? Like 30,000 light years or so, something like this, roughly around. And, we certainly can do seismology in many of the stars in our galaxy, especially the very bright ones. And future missions, like, for example, the Roman telescope, which is going to launch in 2026, is going to be able to do seismology on a lot of red giants in the galactic center, which is about 26,000 light years away. I think it may be possible to do seismology on stars which are even farther than that. So, for example, there are exotic species of stars called blue supergiants, which pulsate in sort of satellite galaxies that sort of orbit our own galaxy in the Magellanic Clouds. There may be ones that are even farther than that, but they'd have to be basically very bright because sort of the farther away that a star is, the dimmer it is, basically to the square, right? So we see things that are pretty far away, but then there are many stars for which it's not possible as well. Thank you.
Yeah. There are a few other questions that I'll just go through. One is, in a two black hole merger, is some mass utilized in the merging of the two singularities? I seem to recall there was some small loss of mass in such a merger that isn't just due to the accretion disk burning through material. So is there a loss when you have when two black holes merge together?
So black holes in general will evaporate their mass, and that could be what this person is talking about, but I don't know of any other mechanism. Oh, okay, actually no, I'm sorry. So actually, when two black holes merge, they'll emit gravitational waves, and this is the reason why we're so interested in this particular type of event, because gravitational waves are a thing we can observe. And when they emit those gravitational waves, they're losing energy. And that energy has to come from somewhere. So the black holes actually do lose a bit of energy. And
part one of the tenets of GR is that mass and energy are equivalent. So they are actually losing mass too.
Yeah, I just want to say, just sort of returning to the idea, I know it's just an idea, but of eviscerating Jupiter. So again, as was mentioned, so Einstein also wrote down this E equals mc squared, which kind of translates between mass and energy. And so, you know, eviscerating 100% of Jupiter to turn into energy would be quite crazy. But in these sorts of mergers, I believe you can convert something like the mass of the sun, which is like 1,000 times the mass of Jupiter, like into pure energy. This is basically what is happening when black holes merge. And it turns out actually that I believe it's the case that like instantaneously when black holes merge, the amount of energy that they're releasing per unit time is briefly like outshines all the stars in the universe or is comparable to it or something like this. So yeah, it's eviscerating Jupiter is sounds pretty unrealistic, but bigger amounts of mass get eviscerated by the universe all the time. So eviscerated is a fun word.
Other questions from the in-person audience? Yeah.
I heard a couple of years ago about a simulation they did on a quantum computer regards to wormholes. Have you heard of that? And if you have, what are your thoughts on it? And I guess another question is, have you heard about the Google Willow chip, quantum chip?
I haven't yet myself. What I have heard about is there are certain analog systems you can build in quantum systems. You can build something that almost behaves like a black hole. So probably you can also build something that behaves like a wormhole. I'm speculating. I haven't read that myself. But definitely there's a lot of development going on recently in terms of building more and more quantum computers. In fact, just last week we had a colloquium speaker talking to us about how you could model the emission around black holes maybe in the future on quantum computers, and what are the challenges for that to be done. And I think at least for sort of the physics that we normally talk about in the astrophysical realm, there seems to be more work to be done just in terms of making it look like more equations that would describe quantum systems. So this is something that people are very actively working on, and we're kind of trying to get there, but we're still a bit away.
There's a question online about the idea of potentially skipping over peaks of localized space-time in order to similarly behave like a wormhole or some sort of superluminal travel. But I'm not sure what peaks of localized space-time necessarily means in this context. Does that ring a bell with?
Maybe it's really like this Krasnikov tube, right? Where you would build something like a hyperloop. If people have heard about this, this idea where you want to build a big tunnel, then evacuate the air, and then go through at very high speeds. And so you could, in principle, think about doing something similar for space time, right? Where you would have a standing warp channel, so to speak, where you would travel along. That's one of the other alternatives that you could build.
There was additionally, how does warp engine placement affect things? You alluded to this a little bit.
Oh, you mean the warp field geometry?
Like, yeah, well,
I think that's ongoing research.
Yeah, would the ship and passengers be effectively immune to the effects of the compression of the warp in front and behind the craft?
So the answer is for the people inside the warp bubble, I think they're fine. For the people sort of hitting this negative mass density region, I think that's not healthy. It's bad. It's very, very bad. Yeah.
Which is why you needed that
because
safety
to use Nicola's words, you would eviscerate yourself pretty rapidly.
Okay. But you were saying it would be hard to steer because you have this warp bubble in front of you, but it's basically outside of your causality, like your cone. So you can't like say, oh, I want to go over to that star now.
You can't. That's right.
And move it because it's actually causally disconnected.
That's right. This
That
is why
sounds like a hard thing.
This is why people have proposed this cosmic hyperloop.
I see, because it's a set.
Then it's a set, and you can kind of go in a
set
loop.
train or
Exactly.
whatever.
And you don't have to steer.
So you just jump on the
Yeah.
train and jump off the train, but you don't have to actually tell it where to go.
Well, you need to figure out the jump on and jump off part.
Right.
But
That
at least
sounds
once you're
hard.
on, then
Yeah. Okay.
you're good.
Okay. Questions? Question. I'll get to you next.
So since you need like the matter and negative energy to fuel the warp drive, is there a point where you just put so much into it to try and make it more efficient that you just make a black hole in it? You just turn it into a black hole?
So the interesting thing about this negative energy is, so black holes have a positive mass, right? What that means is they basically just collapse under their own weight, right? It's like if you build a house of cards and it just falls together. So the thing about negative energy is it goes the other way. So we just fly apart. It's like repelling electric charges, if you've seen that. So you have to do something where you fundamentally break what we think gravity is in order to make that work. Yeah, that's the spirit.
Question back here.
I just want to know, what's the biggest star that we know other than the sun?
So Nicholas, star expert, what's the biggest star that we know about?
That's a good question. So it turns out that stars very, very early in the universe turn out to be like a lot more massive, right? So stars nowadays, like stars that exist today, our sun is about 1 solar mass, and maybe the most massive stars are maybe like a few hundred solar masses, like at the very most massive, right? But early in the universe, you can get stars which are incredibly more massive. The problem is that they're a lot harder to see just because they're so incredibly far away. And also because it turns out, for some reasons I mentioned before, things which are farther back in time are also a lot redder and a lot dimmer. There are some stars like that have very fun names like Arendelle and Godzilla that are like very early in the universe that we've detected. And the reason why we know that they exist is because it turns out there's a quirk of general relativity, which was mentioned, which is sort of like, it's called gravitational lensing. It's sort of like sometimes when you have a lot of mass in some place, it kind of serves as kind of a magnifying glass almost, and it allows you to sort of see things which would be dim, but it sort of like makes them brighter. It turns out that sometimes these really, really massive stars early in the universe, like kind of like very coincidentally lie like at like a very, very precise place, just coincidentally, such that they're like made so much brighter that we can see them. But even then, we kind of see a little spot and we barely know anything about them. But it can be assumed that they're like some of the most massive stars we know about.
Should we do a demo? Right, it's basically like this. What Nicholas is saying is you have, the star here is your black hole, and then the black hole focuses the light. Because one thing that black holes can do, their gravity is so strong that light gets deflected. In fact, light can even, go around the black hole multiple times before flying out. It's really some very, very crazy effect. If you watch Interstellar, the movie, you see this. See like light coming from behind the black hole and going in front. So there you can see what Nicholas just described.
So in short, most stars are kind of like the sun or less massive, smaller than the sun, but there are some that get up around us. They get up to like 100 or so times the mass of the sun. But at really early in the universe, it might be 1,000 times the mass of the sun, something like that.
All right. So this question's a little bit out of scope, kind of, sorta. It's a two-part question. So we're referencing a lot of movies tonight. Have either of you been an advisor, scientific advisor for a TV show, a movie? I mean, you're in Pasadena. You look down the street, something's being filmed. So I figured they'd come to the source for the most credible science, Caltech. So I figured, do you guys have any experience and any fun stories? And my second question is, if we can go down the line, what's your favorite sci-fi movie?
Good questions.
So on the first question, I wish So if anyone out there is watching, I'm interested. So what was the second question? I was too thinking. Favorite sci-fi movie. I'm not sure if this is my favorite sci-fi movie, and it's already very kitschy. But it's probably Interstellar, just because because of my affiliation, and even before I came to Caltech, just because of my profession, just because I have had to watch it like 20 times already. So I am not even close to tenure.
Did you watch it for the 10-year anniversary?
10-year and
you have tenure as a graduate student.
Is that so? For the 10-year anniversary, I may have, but I also have watched it many, many more times than that for less interesting reasons.
So to answer your first question, Kip gets all those jobs. So you should talk to Kip if you want insider stories. My favorite sci-fi movie, actually, I feel like I don't watch a lot of movies, but this one's easy for me to answer. I really like the movie Arrival. It's an interesting premise and also a bit of an emotional story, and it's based on a short story in a sci-fi anthology book that is very good. It's called Stories of Your Life and Others by Ted Chiang, and I highly recommend it. One of the best books I've ever read. That was also a bit of a tangent, but yeah.
Right. I haven't been either, but I know several people who have been. So former grad students here a few years ago, while Interstellar was filmed, were actually set advisors there. And the closest I've gotten to a set was when they filmed the Oppenheimer movie at the Institute for Advanced Study, like right where we're living. They had everything set up outside, and they were like rearranging things and filming at the pond and so on. So at least I can relate to the things that they're showing. In terms of movies, obviously I'm a big Star Trek fan. Goes without saying.
I've been the science advisor on one film, a Disney film that came out a few years ago. And I've helped out on a couple of projects that haven't yet been filmed, but they might be, but who knows? So the film that I was science advisor, it was during COVID, so I didn't actually get to go to the set, but the film was called Crater. It's a film that's kind of like a science fiction version of The Goonies or Stand By Me, these kind of classic adolescents. Somebody's moving away, and so they have one last adventure together, but this took place on a colony on the surface of the moon. And so I was trying to give them advice on how to make it realistic 200 years in the future on the surface of the moon and abide by physical laws. And some of the things that I proposed to them to make it more physically consistent, they listened to, and others they didn't. So I can't be responsible for any physical inconsistencies in the film. But it was an interesting experience reading over the script and then getting to suggest ways to make it better or worse or these sorts of things, help with set design, that sort of thing. My favorite science fiction is probably Contact, that came out like 30 years or so ago. It was written by Carl Sagan, who is a notable physicist and scientist. And I think it's an emotional story, but it's physically accurate, and it proposes, if you haven't seen the film, it's really good. And it's all about what a realistic take on what might happen if scientists discovered some sort of signal from an extraterrestrial civilization. And yeah, I think it's pretty, but Interstellar is awesome too. I really like Interstellar. So that's probably a close second. Okay. One last question, or should we just call it at that? We've got 5 minutes till 10 o'clock. Okay, don't make it too hard because we don't want to stay too late.
Actually, kind of related. Is there like any like science movie or film like kind of grinds your gear? Like this is so ridiculous. Like kind of like it makes you go crazy. Yeah, or just in general, like science fiction movies or TV show. Like, oh my god, the science is so off or so off. That's like the worst trope.
What's the worst kind of science fiction? There's a lot of bad science fiction.
I have to think about this one.
What was the worst one on the movie that you were advising for?
The worst.
Yeah.
The worst thing that they did.
Yeah.
Oh, physically? I never saw the final version, so I don't know if this stayed in. Okay, so there were some interesting calculations that I got to do as part of this. But one that was interesting is at one point they have to remove the helmet of one of the children who's on in order to take a pill, who's on in vacuum. So they're on the surface of the moon. The moon doesn't have an atmosphere, which is accurate. And so but this kid had heart problems and needed to take a pill. So they took off his helmet, which is, you don't want to take off your helmet when you're in vacuum, when you're like, but it turns out you can get away with doing this for a very short period. Have you guys seen the film 2001 Space Odyssey, classic science fiction? At the end of that, spoilers, one of the characters has to go out of the airlock and go to try and get back to Hal, because Hal's, the big bad robot. And he goes into space without his helmet or his suit on. And this is okay for a very short period of time. But one thing that you have to make sure is that you expel the air from your lungs. You breathe out, because normally you'd think, oh, I want to hold my breath. I'm going to hold my breath. But that's actually really bad in vacuum, because you have a lot of pressure when you breathe in, and by definition, there's basically zero pressure in vacuum, and it would cause the differential between the high pressure zone in your chest cavity and the low pressure zone. Essentially, your chest would explode. It would be bad. So the thing that you really want to do is exhale to lower the pressure in your lungs so there's not as much of a differential. And initially, they had him holding his breath, and I was like, don't do that, because that's counter to, it makes, intuitively, you'd think that you'd hold your breath. I don't know if what ended up in the film, because I haven't seen the final scene, but that was, yeah. And notably, there was another really cool scene that I had a part in creating, and that was the idea that on the moon, when a meteor shower happens, of course, here, when a meteor shower happens, it's little bits of rock and dust that are entering into our atmosphere. And as they do, they're traveling at very, very high speeds, and it compresses the air in front of them and ionizes the gas in our atmosphere along that path, as well as the material. So it burns up. So the shooting stars that you see across the sky, that's really just heated up gas and material from these rocks or pebbles or grains of sand that are traveling through our atmosphere. But on an airless atmosphere like the moon, when these things travel in, they're not running into an atmosphere, so they're not glowing. So you don't get a meteor shower in the way that we think about a meteor shower. But what happens is these things travel down, and then they hit the surface of that object, the surface of the moon, and they immediately explode. And so there's kind of a climactic scene where the characters are caught in the middle of a meteor shower, where there's these things, essentially explosions going off on the surface of the ground, where these meteors are coming down and immediately impacting and essentially ablating and burning up as they impact the surface. So that was kind of like a cool thing that they included that I talked about. But yeah, most of it was just like, you need an airlock here, you need an airlock there, you need an airlock there. And it's something we take for granted because we can walk around everywhere here. But on an airless body, you can't get away with that. You either have to have a suit on to keep you under pressure, or you have to be inside of a car or a vehicle or a house or something that has a localized atmosphere, or bad things happen for you.
I want to start by saying a few diplomatic words that we shouldn't really have to say, I suppose. But science fiction doesn't really have to be accurate to be enjoyable, right? Like really, science fiction is just like a new setting for telling stories about people. So oftentimes, you want something to narratively happen in your story, and you may not know that much science, or it may not be possible, or we might not understand enough physics to know whether it's possible. And we still want to tell the story. And I think that's totally fine. And that being said, so I don't know if how many of you were really paying that much close attention around 2012, where it was presumed that the Earth was going to end. And on the back of this conjecture, there was a movie released called 2012, in which actually Caltech canonically falls into the Earth. Like they mention by name that Caltech has been destroyed. And of course, like, this isn't really a spoiler, because they have to somehow explain at the beginning of the movie why the Earth is doing this, right? And they want it to sound vaguely scientific. And so they have one scientist tell another scientist that the neutrinos have mutated and are heating up the planet. And neutrinos, for those who may not know, are like these very light particles that basically barely interact with anything, like trillions and trillions of neutrinos passing through your body like every second, and like almost never interact with you. And so the fact that they could kind of do anything of consequence at these numbers is like kind of ridiculous. I think another example is like maybe another kind of more sensitive movie like Gravity, for example, which is just like, for example, where Sandra Bullock is kind of stuck in space and has to kind of travel between different satellites, which in reality are like very, very far away from each other, such that a human would never be able to do it. The movie also sort of misrepresents like kind of how dense space junk is in orbit around the Earth. But you know, none of these things make these movies bad movies. Some of them can be bad movies for other reasons. But I'm totally happy with incorrect physics sometimes. So.
What was your question, sir?
What would be a NASA file that some of you might be interested in seeing?
A NASA file? I think most of the NASA files are publicly available somehow. Like there's not scientific data for the most part is accessible to everyone. And I know a lot of the NASA material from like the Apollo missions and whatnot is available online. So I don't think there's that much scientific data that's hidden.
So you don't think they lost any? And that's what.
Oh, that's not why we haven't been back to them. I mean, we haven't been back to the moon because there hasn't been sufficient like political motivation to send us back because it's really expensive to go back to the moon. That's the main reason. I mean, we haven't been back in 50 years. We've had the capability for the last 50 years, but we just haven't chosen to do it because it's expensive and a pain in the butt. And we're not competing against the Russians anymore. So, I mean, that's my take on it anyway. But we have reached the end of our night, everyone. Thank you for joining us. Let's thank our speaker. And our panelists, thank you. We will be back in a month, February 14th, Valentine's Day presentation. Bring a date if you want. Presentation all about the explosions from supermassive black holes and the jets that come out of these in galactic systems. And our next Astronomy on Tap is not this coming Monday. It's a week after. It's postponed a week until February 3rd. And that'll be in Old Town Pasadena. And there's the Death Valley Dark Sky Festival on February 21st to the 23rd, and we'll be there. So thanks for joining us. We'll see you guys next month.